This is one of my favorite topics in all of stoichiometry, limiting reactants. It's good real-world chemistry. Now we are talking about the reactant side of the equation, not the products. And this word limiting. This is a reactant that limits how far a reaction can run, how long it can run, how much product we can eventually produce. A great real-world example, driving your car. So your car runs on a combustion reaction. We're combusting the organic compound octane, the gasoline in your car. It's combusting in the presence of oxygen from the air. Okay, so you ask yourself this question, which will run out first? The gasoline in your car or all the oxygen in the air and the atmosphere? And hopefully you would say your car will run out of gas. Maybe that's been you at some point, and we just hope that it wasn't in a scary, dark alley or something like that. But yeah, your car's going to run out of gas at some point before the oxygen runs out of the atmosphere. The reactant that runs out first is considered the limiting reactant or limiting reagent. Same thing. It limits the amount of time the reaction can occur. It limits the amount of product that can be formed. Because when this limiting reactant runs out, the reaction stops. If you run out of gasoline, you can't drive your car anymore. The other reactant is called the excess reactant, or here we might say that oxygen is in excess. In excess. This really is just a reactant that's left over. There's extra oxygen in the air to drive your car for years and years and years. But you're going to run out of gasoline. And without those two reactants, the combustion can no longer occur. So some things to make note of. The limiting reactant is the one that is completely consumed first. It limits the amount of product that can be formed. You may have an excess reactant, and it really will just be extra remaining unreacted. We're just going to have regular old oxygen molecules, O2, and they're not going to be chemically changed in any way because we ran out of the limiting reactant, the gasoline. So here's limiting and excess reactants on kind of a conceptual level. Now let's look more on a particle level. See if we can visualize what this is going to do to my reaction. In the past, we've looked at reactions that are kind of rigged. Like in the lab, things have been present in the proper stoichiometric ratios. For example, hydrogen and oxygen gases react to form water. And so anytime we do stoichiometry, we always need to look at a balanced equation. We're concerned with these ratios between the reactants and products. So here's an easy one, right? We've got, let's see, hydrogen, diatomic, oxygen, diatomic, producing water. We'll balance it. Oh boy, we're going to need 2 oxygens, but now I need 4 hydrogens. Got it. Okay, so we have the balanced equation. Now here's a scenario where we've been giving some reactant. How many molecules of water can be formed in the following scenarios? So we're going to count how many molecules of hydrogen and oxygen are present. Now they're trying to show here that hydrogen atoms are a little bit smaller. They are diatomic. There's 2 together. So in this picture, there's 1, 2, 3, 4, 5, 6. Now this MOL could be thought of as molecules on a small scale. If we were in the lab, we would think of this as moles, because then it's a quantity that I can actually measure by mass. But for now, we can say molecules. And I have 1, 2, 3 molecules of oxygen. So we have a 6-to-3 ratio. In a second, we'll have a 6-to-3 ratio. And then we look at the ratio from the balanced equation. The ratio in the balanced equation is always the correct ratio. Okay, so I have a 2-to-1 ratio in the balanced equation, and I have a 2-to-1 ratio of reactants. It's just on a larger scale. Instead of it being 2-to-1, it's 6-to-3. So the complete ratio in the equation is 2, 1, 2. And I can do that with what I have here. We're just going to multiply everything times 3. So we can go 6, 3, 6. I should be able to make 6 molecules of water. And so if we draw that, I would have my oxygen, so it's a little bit bigger, and then the smaller hydrogen, and that's maybe exaggerated a little bit. 1, 2, 3, 4, 5, 6. On a particle level, we've matched the ratio in the balanced equation. Originally, I had 6 molecules of hydrogen, or 12 atoms, and they're all still present. They're just in the form of water molecules. I had 3 molecules of oxygen, or 6 atoms of oxygen, and they are all 6 still present, but again, now they're just in water molecules. There is no limiting and no excess. All hydrogen and oxygen atoms are present in the water molecules. No limiting, no excess. We have matched the ratio in the balanced equation, and that's great. However, it doesn't always work out that way. Okay, so here's some other situations. Let's count what we have. And again, sometimes I like to just write this in. This is what I have. I've been given to work with. 1, 2, 3, 4, 5, 6 again. 6 molecules of hydrogen, and 1, 2, 3, 4 oxygen. And we want to know how much water we can make. And so again, we're kind of obsessed with the ratio in the balanced equation. And I'm just going to jot that ratio down again, so I don't forget it. Hide that for a second. Let's put it in blue. Okay, so here's the ratio. That's important to all stoichiometry. It's the same equation. O2 producing 2 waters. All right, there it is. That's what I got. Okay, so let's see what we can do here. If we want to react, let's say we want to react 6 hydrogen. Then we need 3 oxygen. We just kind of had that in the previous example. We're always concerned with the ratio in the balanced equation, 2-to-1. If I want to react all 6 of those hydrogen molecules, well, then I need half as much oxygen. I would need 3. Do you have 3? Yes, we actually have 4. So I could even put that in. This is what I have. I need 3. I have 4. Yeah, we could do this. So I could run this ratio from the balanced equation. I could use the 6 hydrogen. I could use 3 oxygen. And then again, if I look at the balanced equation, it's 2, 1, 2. So I could still run 6, 3, 6. I could still make 6 water molecules. That's exactly what we had in the last example. Here's the only difference. You have 4 oxygen, but you're only going to need 3. In the last example, we had 3. It was perfect. This time we have 1 molecule of oxygen left over. Whoa, crazy. All right, so on a particle level, here's what I would have. I'm going to draw 6 water molecules. 1, 2, 3, oh boy, 4. I gotta squeeze them in here. 4. I think we can do this. Thinking. There we go. 5. Hello. And 6. Got it. The difference now is there's 1 oxygen left over. I'm going to put it in blue. So here's my oxygen left over. It's not changed in any way. It's still an O2 oxygen molecule. It's really just left over. It's hanging out. Not chemically reacted in any way. So in this case, we would say that the limiting reactant, the one that ran out, was the hydrogen. All of the hydrogen is now in the form of water molecules, which, by the way, I think one of my water molecules is missing a hydrogen. There we go. The excess is the oxygen, the O2. There's 1 extra oxygen that's just not chemically changed. And that's totally fine. This happens way more than you think in the real world. It's going to happen in the lab all the time. We don't always react things in the perfect stoichiometric ratio. They will always react according to that ratio, but we don't have to start with the perfect ratio. Okay, so check out this last example. And I kind of like to think of it as, what do I have? What do I need? So we're still obsessed with the same reaction, 2:1:2 ratio. So let's count what we have. Okay, so these are the little hydrogens. Here's what I have. Oh boy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I believe. That's a lot of hydrogen. And then I have 1, 2, 3. Easy. I have 3 oxygen. Okay, so let's think about this. What if I want to react all of that hydrogen? Let's use it all up. If I want to react 12 hydrogen, how much oxygen do I need? Well, they react according to the ratio in the balanced equation. It's a 2:1. I always need half as much oxygen. So if I'm going to react 12 hydrogen, I'll need 6 oxygen. Oh, wait a second. That's not cool. That can't happen. Do you see my problem? You don't have that. You only have 3. You would need 6. So this isn't going to work. It's not going to work to react all 12 hydrogen. So I have a hunch then that the hydrogen is going to be in excess this time. So let's try it reverse. What if I want to react the 3 oxygen that I have? What if I want to use up all those oxygen? I know I can't react all the hydrogen. So I look at the balanced equation. I need twice as much hydrogen as oxygen. So I would need 6. And then we just do a little comparison. I need 6 hydrogens. Do I have 6? Yeah, I got 12. I have plenty. I'm not going to use all the hydrogen. This ratio I can do. And guess what? It's the same one we've been doing all along. We just have a different limiting and excess. If we have 6 hydrogen, 3 oxygen, matching the ratio in the balanced equation, I would get 6 water molecules. But this time, here's my excess. I'm only going to need 6 hydrogen, but I have 12. There will be 6 hydrogen left over. Okay, so this is going to look a little nutsy, but here's on a particle level what's present. 6 water molecules, 2, 3, 4, oh boy, 5, 6, and then I'm going to do these little excess hydrogen in blue. Okay, so there are little hydrogen molecules. 1, 2. They're not chemically changed in any way. Diatomic hydrogen, and the hydrogen atoms are just kind of smaller than oxygen atoms. There we go. 1, 2, 3. We'll shove one over there. 4, 5, 6. There they are. This time the limiting reactant is the O2 oxygen. Hydrogen is the excess. All of the oxygen is present in the water molecules. Initially, there's really 1, 2, 3, 4, 5, 6 atoms of oxygen, organized as 3 diatomic molecules. All 6 oxygen atoms are still present on the product side. They're just in a little different form. The excess reactant is the 6 hydrogen molecules that really are just left unreacted. They are extras. So here's what we're looking at on a small scale, on a particle level. Times where we may not have the perfect ratio to match the balanced equation, but we'll always react according to the ratio in the balanced equation. We may just have something that runs out and another reactant that remains excess.